Yeah, as Matt said, it's my last stages of the thesis, and I'm going to present today one kind of analysis that we are doing in our SAR images for deep ice sounding, and these analyses are just constrained to the Doppler frequencies. So we are using this analysis not only in the SAR image finally, but also at the level of the radar data that we collect and any step that we perform in the whole processing chain from the raw data until we have the last results of our images. So what we have with our airborne SAR radar is that we really want to obtain the profile of the ice thickness in Antarctica. So that means that we know the surface elevation, and what we're trying to obtain is the thickness for making a final estimation of the ground profile. That's called the bedrock. That's very important because glaciologists would need to know the whole volume of ice, or even how ice is being discharged from the center of the continent towards the ice shelves delimiting the ground ice. So we have in our SAR image, to this image, the depth in the vertical profile and also the long track distance. So we are performing with the Doppler frequencies. We make the synthetic aperture radar processing, and we have this kind of images with internal layers. And also in this case, we have here at around a depth of 3 kilometers, the bottom of the ice glacier here. But the problem is that with these 2D images, we are not able to distinguish between left and right sides of our aircraft. So we only have the vertical and the long track, but we don't have any kind of information about what's happening left or right. So maybe we are detecting a target coming from the left, from port, and because our antennas are all pointing towards the vertical, we assign this return to the vertical, even it could come from left. So sometimes we have a lot of uncertainties or ambiguities in our results, and these ambiguities mean that we are not having the proper or the true thickness or depth of our target. So what we are having is, instead of only one antenna, we have a set of antennas from the tip of one wing to the other. And when we combine finally all these antennas, we are able to make beamforming and to be able to say whether the bottom is coming from port, vertical or starboard, or even to be able to locate many returns coming from the same range beam. So we are using folded dipoles and a wavelength of 2 meters in free space. That's with 150 megahertz. And as you can see here, the array is not perfectly linear nor uniform. So it has different parts. So we can transmit from port or starboard with an array of antennas. And we receive independently by 12 channels. And these 12 channels, they are not uniformly distributed, but they have, depending whether they are below the wings or below the belly of the aircraft, the antenna separation is different, and also the elevation of the antennas and the long track locations. So that makes the system a bit challenging at the beginning, but we, instead of saying that it's challenging, we like to say that it's giving us a lot of opportunities, because we don't consider the array as non-uniform, but we prefer to say that it's a diverse array. So we can make a lot of several estimations with different channels, and with these estimations we can make a better imaging of the bottom. So for example, in this case, we are receiving by our 12 independent channels. So we have 12 independent images. We make a calibration of any image. We combine them with beamforming or music algorithm, and we estimate the direction of arrival from right, left, or vertical. And once we have this angle and depth, we can make a proper 3D map of the bottom of the ice, so we can obtain a small elevation profile, details, and most important, we reduce the ambiguities that we have in one of these 2D SAR images. So the topics of today are the analysis of the Doppler frequencies that we have, because one of the main problems that we have seen is that once we combine all the Doppler frequencies, so we want to focus all our images, and focusing consists in collapsing all the spread Doppler frequencies into one single point. And when we are collapsing every single Doppler frequency, we have seen that sometimes we have some Doppler frequencies which are present much lower amplitude than the others, or maybe some region of the collected data had some troubles with the receivers or anything. So it's very important that we are able to make an analysis of the different Doppler frequencies. And once we fully understand how each Doppler frequency is behaving, we can make this focusing better, or even identify different features in our glacial representations. And after we have made this analysis of the Doppler frequencies, we could make a proper propagation model of the electromagnetic wave propagation. So finally, we are able to make a better focusing of our SAR images, because usually we are using the pure refraction propagation model, which is completely governed by the Snell's law. But now we have included another possibility, which is diffraction followed by refraction. And in some regions, this new model improves greatly the pure refraction model. So this Doppler decomposition consists, as I said before, in splitting in different bands, the whole Doppler bandwidth that we have. In this case, we are assigning the red, we are taking the negative frequencies of the spectrum and assign these negative frequencies to the red color. We take the near to zero Doppler frequencies and it's assigned to the green color, and the positive frequencies we assign it to the blue color. That's important because depending on how the bottom or the internal layers of our glaciers are, and because we also know that depending on the direction of propagation, we have different Doppler frequencies. These Doppler frequencies will have a greater or lower amplitude regarding others, depending on how can be the slope of the internal layers, the backscattering of the bottom, etc. So we have here one example of the 2D SAR image with the depth in the vertical in kilometers and the long track distance. And this is like well, black and white or gray intensity levels. That's a standard image. So what we make is make the Fourier transform along the horizontal profile. That's for obtaining the Doppler frequencies. And we combine these subbands into a joint RGB representations. So we can see here the colors, and we can see, for example, how the blue color matches perfectly with the positive slopes of the internal layers. The red color, that's the negative Doppler frequencies with the negative slope. And the green one, it's related always to flat surface of the internal layers. However, if we look to the bottom, that's the profile of the ground of the continent, the rock, the bedrock, this is mainly white because that's combining the red, green, and blue colors, because we don't have a unique direction of arrival here, but the backscattering is in many directions. So these many directions are combined into white color. So we can even distinguish the surface, the surface interface between air and ice here at 0 kilometers. It's going to be mainly green because it's very, very smooth, almost flat. And we compare this smooth, flat green surface with the rough white surface from the bottom, we can distinguish exactly where the bottom is and make the difference maybe regarding possible multiple echoes from the surface. This is another example of the Doppler decomposition that we have applied. So this line is the surface. Here we are above sea level. So the zero horizontal level is not the air-ice interface, but the air-ice interface here is here in this case. And this is the bottom. But now I wanted to pay attention here to what's happening on the surface. So we see here clearly some internal layers which are more or less horizontal regarding the surface, so they are appearing in green. And here we see shallow crevasses, or even also surface crevasses, which act like a corner reflector. So they are scattering in multiple directions the signals that we are transmitting from our airborne radar. So we are able to directly assign to these white colors in the surface to the crevasses. And when we have mainly green colors, red or blue, they are internal layers. So that's one of my favorite images, because we can really see really well these shallow crevasses here. So the kind of flights that we are performing above Antarctica, they are very, very close to the regions between grounded and floating ice. And we are also focusing in regions with high or very high flow speed in the surface of the ice, discharging from the center of the continent towards the floating ice. These regions are very important because depending on the slope of the bedrock, of the ground, the thinning rate of the glaciers can be accelerated or it can be more stable. And not only because the profile or the slope of the bedrock, but also because there are water conduits which are making that the surface and below the surface of or even glacial or basal melting in the ice shelf areas, ice shelf glaciers. And these water channels are melting and they're accelerating the thinning rate, or even they can make that the ice shelves are collapsing. So we are paying much attention to these regions close to the grounded and floating ice, and above all when the flow speed is very high. This is one of the examples of these images. So we have the 2D SAR image, vertical with the depth and on track distance. And we have different locations where we can say whether our aircraft is going along the flow of the ice stream, like here. Here we turn, and now instead of going along, we are going across the flow of the ice stream. And also we have different regions where the glacier is in touch with the ground, with the bedrock, and here the ice starts floating above the or floating in the sea level. So if this is the ground, and we can see here this kind of hyperbola that represents the different water channels, and they are different depending on whether we are along flow or across flow. So now we want to pay attention to the limit between the ice stream area with very, very high flow of the ice, which can be around 1 kilometer, maybe close to this area, and here, where the ice is very steady and it's maybe 1 meter per year. So if we give a look here to this 2D SAR image, we don't really appreciate any difference in the internal layers. But when we make this Doppler decomposition and assign the colors to its Doppler frequency, we see that in the area with a high flow speed, we are not able to see any pattern in the colors. But in the area where the ice is flowing with a very, very low rate, we are able to appreciate the different Doppler colors. So we call these regions unstructured ice because we are not able to see any kind of layer formation of the internal layers. And we call these regions with the Doppler colors are structured ice, because we can say that these internal layers have different shape or profile. And so that's also important because we can even be able to draw an internal profile of the region separating high flow ice and low flowing ice. Usually we have these measurements from satellites or even airborne measurements, but they are measurements at the level of the surface. So we don't know what's happening below that surface. So for example, we can say that maybe the lateral margin of this ice stream is not vertical, purely vertical, but it has like a kind of a slope. We are now studying how accurate can be these regions or not, but we think that, or I think personally that they can be of importance for glacialists. So they can say whether an ice stream is limited by a vertical or kind of different profile. And we have here another kind of example. So we have, this is not a SAR image. So we have here depth and along track, but at this moment of the processing, we made only range compressed signals because we are transmitting chirps. So at this step, we only make the range compressing step of the whole processing. So now we don't have any kind of along track focusing or synthetic aperture radar processing. So it's only range compressed. So we have the radar data and we have this envelope corresponding to a channel, and please don't pay attention to this. These are points from other work. So forget about this. So just pay attention to this profile. And as I said before, we can apply this Doppler decomposition not only to the final stage of the SAR processing, but also to the range compress step. And we can see here how these Doppler frequencies are being collected. So first we have here in the left branch, the upper levels of the hyperbola are blue, then green, and then red. And when we are in the red branch, we have the shallower profiles are red, then green, and then blue. So what we want to make after we are able to make the long track processing, it's to be able to collapse this blue, green, and red into one simple branch or one single branch. And the right branch, we want to collapse the red, green, and blue into one. That's the more or less the informal definition of the focusing. So collapsing all Doppler frequencies in one single point. This hyperbola is not the typical that we see from a point target in the synthetic aperture radar field, but because this is not a single point, this is like a collection of points coming from a water channel from beneath the ice glacier. So we would have here one point target, here other point target, other. So this collection of point targets follows more or less a hyperbola. So this is a hyperbola made of hyperbolas. So it's not from a single point. So when we make the SAR focusing, we have something really horrible. So instead of collapsing the blue, green, and red into one single profile, what we are making is the opposite. So we are moving this red frequency towards the left, but so much that we are unfocusing. Rather than focusing, we unfocus in this step. Even we want to make a SAR processing, we make the opposite effect. So we didn't know why was happening, and so we thought that maybe the collection was wrong of the data here, or that the data was organized in a very weird manner in reception or anything. So we called other groups, and they gave us their own processing software, and we processed with their scripts and everything, and we got the same image. So we started thinking that maybe there was happening something different in these areas. If when we are trying to go from the range compressed to the SAR data, we have an unfocused image. And the explanation is that when we are using our propagation model, it is always based on the pure refraction, and we are following the Snell's law Snell's laws. But it happens that this Snell's law, they are not considering absorption losses, nor polarization, or anything. So they are just based in this informal principle of the fastest path from transmitter to receiver. So in case that we have an structure internal layers, as we saw before, it's this region where we can define or we can infer that, because if we are able to see a pattern in the color of the Doppler decomposition, we can say this structure. So in these regions, we can apply the refraction, pure refraction, and the image is focused well. But when we are in a region where we can't say anything about how internally these layers are organized, and we call these regions a structure, if we apply this Snell model, is not working really well. So instead of assuming a pure refraction, we decided to apply some crazy models. So the first one was a vertical propagation and then a slant towards the target of interest. And so here in the air-ice interface, we rejected refraction, and we thought that maybe some kind of diffraction was occurring. So imagine, for example, that we have a crevassed region of the glacier, where the ice is so broken, so horrible organized there, that we can have a kind of diffraction grating. So we are having lots of secondary propagation points of our wave, a lot of scatterers. So we can have many different propagations. Other kind of option is slant propagations and vertical within the ice. So slant in air and vertical within the ice. So we tested these different models for focusing our SAR images in these unstructured areas. And we found that, as expected before, as I saw before, in this area, for example, that was horrible, and that corresponds to the Snell laws equations. And here we tried vertical in air and slant in ice. It worked more or less, but not really well. And we finally tested this slant in air and vertical in ice, and it worked very well. So all the Doppler frequencies collapsed very well, and we obtain a well-focused area. So when we were comparing the different Doppler apertures or illumination apertures with pure refraction model and with the diffraction followed by refraction, we saw that these apertures, these beam widths, the beam width can be the same if we have the same Doppler frequencies, but the aperture is much different. And after we made that, we arrived to the result that we were focusing better. So we have here another subglacial channel. And after the range compression, we see how still we can see some patterns of the red, green, and blue colors of our Doppler. When we apply the pure refraction, we are not focusing, but I'm focusing. And however, when we apply the diffraction followed by the refraction, we collapse better our frequencies. So that's what was happening in unstructured ice. And on the contrary, when we are applying this new model in the structured ice, it's working worse. And here in these areas, this diffraction followed by the refraction is not working well, and we have to apply the classical refraction model. So that makes that before processing our images, we need to know a bit more about how these shallow internal layers are organized. Because depending on that, we can say whether we have an structure or structured ice and apply pure refraction or diffraction followed by refraction. And that's one of the new things that we have made in the thesis. So we need to say something before we are able to process. That has sense because in other kind of applications, we know, for example, the digital elevation model. We want to make ground SAR imaging, and after we know the digital elevation model, so we can apply different processings, or we can make different interpretations just to avoid the layover of the mountains or these kind of things. And in this case, it's the same, but not for the layover, but for knowing which is the best or the optimal propagation model. So in the conclusion, we can say that this decomposition is important, not only at the stage of the SAR image for being able to interpret what's a crevasse or what not, or even the lateral or bottom margins of the ice streams, but also at the radar data level at the beginning of the processing. So we can know whether we are in structured or unstructured ice, and depending on this identification of the region, we can apply finally pure refraction or refraction model. And this can result in a much better focusing. So we have also, if our single SAR image is better processed, we can obtain better direction of arrival estimations. And with this direction of arrival estimations, we can obtain better thickness, 3D thickness of our regions under study. And that's all. Thank you very much.